All right, let's go through some examples of molecular formulas and how to go about determining if they're polar or not. What you can't do is just look at it. There's no way unless you've memorized the shape. So what you're going to need to do in each case is draw the Lewis structure. Without the Lewis structure, you've got nothing. Now, if you need help drawing the Lewis structures, please go back, watch those videos. But for right now, I'm just going to go ahead and give you the result of the picture. So my first picture is OF2, oxygen difluoride. Now, if I draw oxygen difluoride, this is what oxygen difluoride looks like. An oxygen in the middle, two fluorines, and two lone pairs. Now, to figure out the polarity, don't just look at this and go, oh, it's symmetric, nonpolar. No, 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 no. You need to get the shape. So if I look at my oxygen in the middle, the oxygen in the middle has 1, 2, 3, 4 domains. I need to sketch a chicken foot. I'm going to go ahead and sketch my 4 domains like this. Now, 2 of those domains are lone pairs. So I'm going to go ahead and ghost out 2 of these domains. This is not a symmetrical molecule. The pull of this fluorine on the electrons does not cancel the pull of this fluorine on the electrons. Since it is not symmetric and there is going to be an overall pull, this molecule is polar. All right, let's go ahead and look at chlorine trifluoride. So the Lewis dot structure for chlorine trifluoride is 1 chlorine with 3 fluorines, each with their individual lone pairs here, and that chlorine has 2 other lone pairs on its center. Now, no matter how you drew this, we need to look at the actual symmetry of this. So look at your domains. This chlorine has 5 domains, 1, 2, 3, 4, 5. Each lone pair is a domain. For 5 domains, I sketch 1 up, 1 down, 3 in a ring around the middle, a trigonal bipyramidal structure. Now, as for our ghosts, we have 1, 2 lone pairs, 2 ghosts. They need to be ghosted out in the middle, the roomy equatorial position. So when I ghost 2 of these out, I get a T shape right here. This is not symmetrical. Top will cancel bottom. That's true. However, there is nothing to cancel out the pull of this fluorine on those electrons. Since it's not symmetrical, this is also a polar molecule. All right, let's go ahead and take a look at ammonia, NH3. NH3 will have a nitrogen, a hydrogen, another hydrogen, and a lone pair of electrons. Now, whenever you have just 1 lone pair, you are absolutely going to be polar. But let's go ahead and look at that polarity. You've got a nitrogen at the center of a 4-domain molecule, so a tetrahedron. We've got hydrogens on 3 of those corners and a lone pair on the top. This nitrogen is going to be pulling electrons away from the hydrogen because nitrogen is more electronegative. So is it going to pull away electrons from those hydrogens. And then we have electrons on top. The electrons are all shifting towards the top of this molecule. This top of the molecule is going to be very negative. We're going to have a negative side, and this side is going to be positive. This is, in fact, a polar molecule. All right. Boron trifluoride. If you draw the Lewis dot structure for boron trifluoride, you should have a boron with 3 fluorines. Now, do not force boron to have 4 bonds. It's an exception. Boron only gets 3 bonds. Many people will look at this Lewis dot structure and go, it's not symmetric. It's going to be polar. Left cancels right, but there's nothing to cancel the top. If you do that, it's because you're not thinking about it 3-dimensionally. So this is not a 90-degree angle. 1, 2, 3 domains will go into a Mercedes sign configuration, a trigonal planar configuration. So with a trigonal planar, the pull of the fluorine upwards will cancel the pull of the fluorines to the other two corners. This is a three-way tug of war. Nobody wins. It's a symmetrical molecule, and therefore it is non-polar. All right, we're going to keep going. ASF5, I'm going to get a different color here. So for ASF5, what we've got here, if we draw the Lewis structure, is arsenic with 5 fluorines, all at the corners of a trigonal bipyramidal structure. No lone pairs on my middle arsenic at all. So I'm going to redraw this. We've got, let me draw it over here, 1 up, 1 down, 3 in a ring around the middle. 5 domains, 1, 2, 3, 4, 5. The upward fluorine will cancel the downward fluorine. The 3 in the ring are all going to cancel each other out, a three-way tug of war. So this arsenic pentafluoride is non-polar. Okay, it looks like I'm running out of room a little bit, so I'm going to grab another sheet of paper. And let's go ahead and do carbon dioxide, CO2. If you draw the Lewis structure for carbon dioxide, it looks like this. Now, some people think that's 4 domains around carbon. It's not. A double bond is 1 domain. Another double bond is 1 domain. 2 domains. This is a linear molecule. So oxygen is going to pull electrons towards it. This oxygen is going to pull electrons towards it just as hard. There will be no winner. This is a symmetric molecule, so it is non-polar. All right, 3 more. XeF2. If you draw the Lewis structure for XeF2, you're going to have a xenon with 2 fluorines attached to it, and there's 1, 2, 3 lone pairs. All right, let's check out the symmetry. Xenon has 1, 2, 3, 4, 5 domains. For 5 domains, we draw 1 up, 1 down, 3 in a ring around the middle. I'm going to go ahead and put my lone pairs on the roomy equatorial middle. So I ghost out all 3 in the middle. This gives me the symmetry that I need to call it non-polar. My top fluorine will cancel out with my bottom fluorine. The 3 lone pairs, all at 120 degrees, have a symmetry that will cancel out. No one wins the tug of war, non-polar overall. Now, what about XeF4? If we draw xenon tetrafluoride, you're going to have xenon with 1, 2, 3, 4 fluorines attached to it with their lone pairs. And then you will still have 1, 2 lone pairs on xenon. Now, the way I drew it, it's hard to see the symmetry. So let's go ahead and draw the actual picture of this 3-dimensionally. We have 1, 2, 3, 4, 5, 6 domains. For 6 domains, we're going to sketch 1 up, 1 down, 4 in a ring around the middle. Now, up to the ring is 90 degrees. A ring split 4 ways is 90 degrees. It doesn't matter who you ghost. I have 2 ghosts, 2 lone pairs. I'm going to ghost out my top, but it does matter where we put the second ghost. I'm going to ghost out my bottom. This is symmetric. Top lone pair cancels down lone pair. A pull to the back cancels with the fluorine pull to the front. A pull to the right fluorine cancels with a pull to the left. It is no pull overall. And even though we have polar bonds, this is a non-polar molecule. All right, my last one, bromine pentafluoride. So for bromine pentafluoride, if we draw it out, we're going to have 1, 2, 3, 4, 5 fluorines attached to the bromine. Each of those fluorines will have its complete octet. If we take the time to count our electrons, fill in the outer sides, and then we're going to have 2 leftover electrons on our center. That gives me 6 electron domains. I'm going to draw out 1, 2, 3, 4, 5, 6 electron domains. One of these is a lone pair. Anytime you have one lone pair, it's not going to be symmetric. There's nothing to cancel it out. So therefore, this will be a polar molecule. I hope that helps. Take care.